So here I am, sitting on the lava delta from the 1953 eruption of the San Benedicto volcano that you see in the back here. This volcano erupted about 70 years ago or so, during about 3 months. In the first 2 months you see that enormous pile there that erupted as ashes. You can see the ash layers in the mountain. Ashes, pumice, volcanic bombs, very explosive volcanism. It took about 2 months, and after about 2 months there was lava coming up through the crater pipe, and it burst through the side of the volcano. You can see that there. And through the side of the volcano it burst out, and then this enormous pile of blocky lava started to form in the last month of the eruption or so. And we are here with 10 people, and we're trying to do everything with this volcano that you can do as a geologist. Clearly, one of the most important things is that we want to figure out whether this volcano can erupt again, or it can erupt again, but how violent it will be. Not too long ago, in January of 2022, there was this enormous eruption of Tonga, of a volcano in Tonga. And that created a tsunami, and that tsunami is very dangerous. I mean, if this volcano erupts, there's not going to be a lot of people involved directly because there's nobody living on this volcano. But 400 kilometers or so to the west of here we have Mexico, and in Mexico there's a lot of people living on the coast, and they don't like the tsunami that this thing can generate. So we are trying to figure out, the volcanologists that we brought with us are studying the eruptive behavior of this volcano and the ashes that come out of this thing, and the chemistry to assess how violent it could be. But there's much more that we can do here. One of the big questions is, why is this volcano so explosive? It's a bit strange, because we are sitting on a mid-oceanic ridge, and at mid-oceanic ridges typically magmatism is very calm. The volcanoes of mid-ocean ridges in the Central Atlantic, for instance, are 3 kilometers deep. There's a little bit of lava coming out, making some nice pillows, and there's no explosions or nothing. Those explosions you find typically in settings of subduction volcanism. What happens there, like in Tonga, like in Mexico, like in Guatemala. So what you have there is that there's a plate going down into the mantle, and the plate brings with it sediments that are formed in the ocean, sediments that are sandstones that come from land, and a lot of water. And that water and sediment go into the mantle, and they change the chemistry, and they add the water to the mantle, and the mantle then starts to melt and makes very explosive volcanism. Now, one of the things that we think is going on here is that in the mantle underneath this volcano there is such subduction influenced mantle. Those things we call mantle wedges, and those are the parts of the mantle that are contaminated by all those sediments and water. And that is not because of active subduction, because there is no subduction here. The nearest subduction zone is hundreds of kilometers away and dipping away from us, so that's not going to do anything here. But it might be subduction that occurred here about 180 million years ago. 1,500 kilometers below our feet is, in the mantle, a subducted plate. It's a big plate that is slowly sinking through the mantle, and has been doing so for 180 million years. And when that thing went down, it made subduction volcanism. And the volcanoes that it made in the Jurassic are now located on Vancouver Island, thousands of kilometers to the north of us. They drifted there with plates in the course of the tens of millions of years. And we sampled those to see what kind of sandstones would have been brought into the mantle when those volcanoes formed. And we think that those sandstones are still sitting down below our feet here in the mantle. And these lavas that we see here, they formed at about 70 kilometers depth below the plate, in the location where those sandstones and where that chemistry should have been brought down when that plate that is below our feet was subducting. And if we find them, we can find them in the chemistry. We can find them in the chemistry, for instance, of small minerals that are in these rocks that are called olivines. And there might in these rocks also be zircon minerals, and the zircon minerals are little sandstone, are parts of a sandstone, and we can still find them, we can still date them. And what we think is that the zircons that we might find here are way older than this volcano or the plate that we're sitting on, which is only 2 million years or so, and are the same as the ones that we find in Vancouver. And if that is the case, then it means that the mantle that was contaminated by the slag that is far below our feet is still sitting below our feet and has not moved. And if that is the case, then it means that the convection in the Earth's mantle, even in the Earth's upper mantle, is much slower than we ever thought. And that would be a major step to come closer to the question, what drives plate tectonics? And that is, in the end, what this thing is about. That's the reason that I assembled this team to go here and test it. But while we're at it, we might just as well do everything that we can do with a volcano. And one other thing that we can do is studying the magnetic field, because these volcanic rocks, these black rocks that you see everywhere, are fantastic recorders of the magnetic field. So we have sampled today with Kwame Meyer, PhD student who is down there near the ocean. We have sampled rocks here to study the direction and the intensity and the strength of the magnetic field that is contained in these rocks. And that is what we will do here, and also farther to the north on the island, and on the island of Socorro to the south of us. So that's what we're doing here, but mostly we are massively enjoying ourselves and finding ourselves the most lucky geologists on this planet.